All right, so I'm Alex Turner, a third-year graduate student at Harvard University, and today I'm going to talk about estimating urban carbon dioxide fluxes using a dense surface network. So there's a couple ways we can estimate urban CO2 fluxes. On the left, I'm showing what's known as the bottom-up approach, where you take emission factors like the CO2 per car and activity data like the traffic density, and the product of these give you a map of US traffic emissions. So these bottom-up estimates relate the CO2 emissions to the underlying physical processes. However, they can be subject to substantial uncertainties. On the right, I'm showing what's known as the top-down approach, where you measure CO2 concentrations in the atmosphere and then try to infer what the most likely sources are leading to those observations. And this top-down approach is typically done in the context of a bottom-up inventory. So what that means is you typically use a top-down approach to infer where a bottom-up inventory is over or underestimating. And top-down methods have typically relied on sparse networks to measure urban CO2 fluxes. However, today I'm going to talk about using a dense surface network in the Bay Area. This network is called Beacon, and it's a dense network of moderate precision nodes, and each node costs about $5,000. For comparison, a high precision instrument might cost anywhere between $50,000 and $100,000. A Beacon node measures CO2 to about plus or minus 7 ppm, and future nodes are going to measure CO, NO, NO2, ozone, and PM at 1 hertz. And so this map up here shows the 22 Beacon sites, and for reference, we're all here in the Moscone Center. So these 22 sites shown would cost about as much as 1 or 2 high precision instruments. So as I mentioned, the top-down approach typically uses a bottom-up inventory as well. So there's 2 complete CO2 anthropogenic inventories that I found, the EDGAR inventory at 0.1 by 0.1 degree resolution, and the VULCAN inventory at 10 kilometer resolution. And in the mid-latitudes, these are comparable spatial scales. So the first thing I did was plot up what EDGAR looked like over the Bay Area to see how much information it was actually giving me. And EDGAR is not time-resolved, so this is actually an animation. But there's not really a whole lot of information provided at the spatial scales we're interested in the Bay Area. So instead, I decided to look for other information about CO2 in the Bay Area. And I found that the Bay Area Air Quality Management District provides county totals. So transportation is the biggest piece of the pie at about 37%, followed by industrial and commercial at 36%, then electricity and cogeneration, residential fuel usage, et cetera. But they also give you a table of point sources in the Bay Area. So the largest sources in the Bay Area are, not surprisingly, oil and gas refineries. So Shell, Chevron, Tesoro, ConocoPhillips. But there's also some more, I guess, exotic sources, such as the Jelly Belly Candy Company at 1 Jelly Belly Lane, which is the 170th largest source in the Bay Area. So if we go back to the pie, these point sources represent most of the industrial and commercial and electricity cogeneration sources. Then I took the 7% of residential fuel usage and mapped that to population density and gave it a temporal dependence based on temperature. Then for the transportation sector, Brian Mcdonald developed a very good 5 traffic inventory, or transportation inventory, that has up to 500 meter resolution in the Bay Area with a diurnal cycle over a course of a week. So this gives me a high resolution anthropogenic CO2 inventory for the Bay Area. However, I still need to take into account natural fluxes. So for the moment, what I've done is taken natural fluxes from Carbon Tracker, spatially interpolated those to 1 kilometer. And then I also wanted to extend the region to potentially, or in case our measurements were sensitive to larger than just the Bay Area. So what I did was I used EDGAR or VULCAN, spatially interpolated to 1 kilometer, and Carbon Tracker. And then I say that this coarser inventory should match my high-resolution inventory inside this box. So by doing so, I impose the diurnal cycle for my inventory on this coarser one, and I then have an hourly 1 kilometer CO2 inventory that resolves physical processes such as traffic for California. Great, so now going back to the observations. What I'm showing here is 3 months of Beacon observations, and each color is a bit different Beacon node. There's a couple things you can notice. First, you can notice a prominent diurnal cycle at all the sites. And you also notice very large CO2 spikes of more than 100 ppm at multiple sites, for example, right here and later on in October. So what I wanted to do was, so I can look at the diurnal cycles in more detail by taking the monthly mean diurnal cycle for September. And so what I'm showing in blue is the monthly mean diurnal cycle for Arbor Vitae, located here, and Sequoia up in Richmond, California. I've also tried to simulate the CO₂ concentrations at these sites using WRF-STILT and my prior inventory that I put together. And it seems like we're able to do pretty well at these two sites. We capture the nighttime pretty well. We see the morning rush, then the diurnal cycle, the PVL height increases, CO₂ concentrations decrease, and then we return to nighttime levels. And this is represented pretty well at both Arbor Vitae and Sequoia. However, there are some sites that we don't do nearly as well at with this prior inventory. For example, Ironwood, we capture the nighttime decently well. We see a bit of the morning rush, but then there's this huge CO₂ concentration in the middle of the day that's not captured at all by the model. Conversely, at Jack Pine, which is located over here closer to the mountains, we see that we get the midday concentrations somewhat well. We get the decrease, but there's this large nighttime concentration that we don't capture at all. So what I'm really interested in knowing with this is what can Beacon actually tell us about CO₂ fluxes in the Bay Area? And in order to answer this, I decided to do a simple one-day test with Beacon to see if I can actually estimate anything with the Beacon network. So for the rest of the talk, I'm going to talk about just a single day of Beacon data from September 1st, 2013. And in order to estimate those fluxes, I need to know the footprint of those measurements. So what's the spatial area that those measurements are sensitive to? So in the bottom right here, I'm showing the mean footprint for all the sites on that day. And we can see that Beacon is sensitive to most of the Bay Area, most of the Eastern Bay Area. So these footprints can then be used in an inverse modeling framework to infer CO₂ fluxes. So then I simply used a Bayesian inference approach to estimate the CO₂ fluxes using my prior and the Beacon observations. And that's what's shown on the left here. So we have hourly CO₂ fluxes at 1 kilometer resolution using a WRF-STILT inverse modeling framework. What I think is most interesting is what's plotted on the right, which is the difference between the posterior, the estimated fluxes, and the prior, which is the inventory that I put together. And so you can see some pretty large changes occurring, but it's difficult to really, tell based on this animation. So what I did was I summarized it by showing the mean over this day. And there's one thing that really stuck out to me, and that's this right here. This is the Bay Bridge in California, which some of you probably drove across to get here. And what this is really saying is that there were almost no CO₂ emissions on the Bay Bridge on this day. And when I saw this, I thought, well, that was fun. Looks like something's totally wrong and probably can't get anything out of the data. So I investigated a little bit more before totally giving up, and what I found was, I think, pretty interesting. The day I was looking at was September 1st, 2013, which is the day that the Bay Bridge was actually closed to convert from the old bridge to the new bridge. And so what was important from this is that it wasn't just that the measurements weren't sensitive to the Bay Bridge, because we actually had a diurnal cycle on the Bay Bridge in the prior. The measurements were showing that there were no emissions on the Bay Bridge. And so this seems to be consistent with known fluxes in the area. There shouldn't have been any emissions because it was closed. So it's pretty much the best natural experiment I could have asked for as an inverse modeler, like shut off emissions in an area where there's a large source and nothing else, and can we capture that? And it seems like with this dense surface network, we were able to capture it, which I think is pretty cool. So then the obvious next step in this work is to extend this record to use more than just a single day of data and look at some of these later periods. For example, in the month of October, there were BART labor strikes, which could have caused large congestion in the Bay Area and might have shifted the diurnal cycle. And we should see if we can test if we can see that with our network. Additionally, we're looking into defining some directional covariance matrices for this inversion, because at these fine spatial scales, you're going to be correlated along, say, a road, but as soon as you go off the road into, say, the ocean, you're not really going to be correlated anymore. So we're going to represent that in our covariance matrices. So in summary, we constructed a detailed CO₂ inventory for the Bay Area at 1 kilometer spatial resolution. We developed a WRF-STILT inverse modeling framework for Beacon, and we demonstrated that Beacon seems to be sensitive to local urban processes, including traffic, that are roughly consistent with some known processes. What I really want you to take away from this talk is that dense measurement networks are a valuable tool for understanding urban greenhouse gas fluxes. And with that, I'll take any questions. Thanks.
Ken.
I haven't looked at just the daytime yet, but that would be interesting to look at. Yeah.
I would caution you about the ability of coarse stilt to accurately simulate the boundary.
All right. One thing I am hoping to do in the coming months is do a more comprehensive evaluation of the boundary layer heights and wind fields in the Bay Area, but I'm currently looking for any sort of boundary layer data I can get my hands on. So if anyone has any, I'd be happy to talk with you about that.
Other questions? So I have one. I think everyone agrees that denser measurements are important, but I think it's somewhat controversial. Or the question is, what's the trade-off between measurement density and precision and other sources of uncertainty? So have you done a formal uncertainty assessment, and what would you predict? Or have you, with your framework, what would you predict the trade-offs would be between the traditional high-precision approach and this coarse precision denser network?
So this is something I was actually planning on talking about when I first submitted the abstract. And we are, oops, sorry. Whoops, oh well. Anyways, I was gonna be doing OSSEs to basically test this. So I'll use my high resolution prior that resolves processes such as traffic, run that forward with WRF-STILT, and then try and retrieve that using one of the other inventories like VULCAN or EDGARv, and see how well we can do. And then what I was gonna do is vary the number of sites I use and vary the measurement precision at those sites, and we should be able to quantify what's the trade-off between measurement precision and measurement density over a variety of sites, and yeah, basically test that parameter space. But I haven't done that yet.
Thanks again.